than the 1.5 meters per second squared we had before. Because now friction is now helping you stop it. You get it? Okay. Can we continue? Do you think this is going to be useful for people who are absent? Well, if they don't watch this video, I'm going to have to, I don't know. Yeah, we're going to skip corporal punishment and go right to capital. We got it on video now. It's true. Okay, and if it's published on the internet, you know it's true. Right? Okay. What if we had a person standing in an elevator? Whoops. They're going to have long legs. They're standing in an elevator.
Why are they doing it slow?
We don't know. But we do know that the elevator is going to rise with an acceleration of 3 meters per second squared, and this person's going to have a mass of 50 kilograms. Whoops.
What floor are they on?
Doesn't matter. We're accelerating upwards. My question to you is, can you draw a free body diagram for the person?
How much does the elevator weigh?
I'm not interested in that. I'm interested in the forces acting on the person. What are you going to draw? No velocity. Velocity is not a force.
You got force acting down.
I need a force acting down. What is it? The weight of the object. How much will this guy weigh? 490 newtons. Right? If that was the only force, this guy is going down. So there's got to be another force. What is it? The floor pushing up. Why did I draw that force bigger than that force?
It's accelerating upwards.
It's accelerating upwards. That force has to be bigger. Is there anything we can do to calculate that force?
Yes.
F equals ma.
Wait, how have these the
Don't care.
Oh my God.
Give me a, what do I write in there for F? Isn't the Fn going up? Everybody okay with that? I'm going to write Fn.
minus
What's going down?
490?
490. Everybody okay with this? What are we plugging in for the mass? 50. Do I care about the mass of the elevator? I'm only focusing on the person. You get it? 50 kilograms times what?
3.
Oh, we have an acceleration of 3 meters per second squared. Could you calculate the Fn now? What is it? 640 newtons. Can somebody tell me what this guy normally weighs? Ah, that's his mass, 50 kilograms. What does he actually weigh? 490. So if he was standing on a bathroom scale here, what would the bathroom scale normally read if the guy didn't accelerate upwards? 490. What does that bathroom scale read now? So what does he feel in the elevator when the elevator starts to accelerate him upwards? Does he feel heavier? Yes. Have you ever experienced that in an elevator? Well, let's see if that's really for real. Are we ready for a live demo on YouTube? Okay, I know I can do this. Don't help me. There we go. So this thing weighs about what? About 10. What if I wanted to accelerate it upwards? Would I just pull with 10 newtons? I'm going to have to pull harder than 10. Let's see what happens to the scale reading when I try to get this thing to accelerate upwards. Are you ready? Did the needle go to a higher force? The moment I pull on this thing to get it to go up, watch the needle. It's shot to 14. The moment I get it started, it's shooting up. Okay, you guys don't believe me? Did you see it? Are you telling me you don't see it? I didn't rig it. I'm pulling and the needle shot up. Now, what's going to happen if I was going to raise it at a constant velocity? It's going to stay the same because the acceleration is 0. What if you have 0 acceleration? Your net force is 0. Force is up, force is down, right? But what if I want to get the weight to come to a stop when it goes up? What force, I don't want to lose you, what has to be a bigger force? The weight pulling down or the spring scale pulling up as this thing comes to a stop? Weight's got to be bigger than the force going up. Let's see. So that means the needle should get heavier when I start, but when it comes to a stop, the needle is going to become lower. Ready? Did it do it? Okay, I'm going to do it bigger.
Oh, that was like.
Did it do it?
Yeah.
Okay, so that's what I'm trying to say here with our elevator. If that force is bigger than that, the acceleration is up. What if the force was the same? What if the normal force was equal to the weight? There'd be no acceleration, right? And now what if the force normal was smaller than the weight? Sorry, I just wrote it the other way around.
You'd be going dropping.
Well, it doesn't necessarily mean he's going down. It just means the acceleration is negative. It's down. Does that make sense? Could you be going up with a negative acceleration? Yeah, that means you're slowing down. Now, what if we were at the top floor and now I want to have this thing start to come down? What am I going to do with the elevator? Push as hard as I was before? I'll push less. If I push less, then gravity is bigger than the force going up. This thing's going to accelerate down. What happens when you're coming down in an elevator and you want to stop at the bottom? What will the floor do? It'll push harder going up to bring you to a stop. Does that make sense? Okay, so now what I want to know is, how many times heavier do you feel than normal in this circumstance? You're going to take these numbers and divide one over the other. 1.3, you know what you call that?
G.
That's your number of G's. Now that's my own symbols. They call it G-force or G-factor sometimes. Did you ever hear about this? You had a great adventure. Oh, you're going to be on 3 G's on this ride. And you say, great, I can't wait to pay a fortune, right? And then wait in line for 2 hours, right? Okay. This is your number of G's. What this is called is your apparent weight. That is your normal weight or your actual weight. If you take your apparent weight and divide by your actual weight, you get the number of G's that you're experiencing. Yes, Nick?
They use that on cars with suspension, right?
They use it, yes, all the time. We'll talk about lateral G's in a second. Okay, are you ready for this?
Parabolic arcs.
We are going to do a formula now. We're going to work on this. We're going to say that the number of G's is equal to the normal force divided by the weight. What do I plug in for the weight? What? Well, I don't mean the number, I mean a formula. How about mg? Is that good? Can you figure out by using the algebra to calculate, to come up with a formula to put in for Fn? What's this?
MA.
MA. And now I gotta bring that term over. What is that? Bring that over. What is this term? FW. That's gonna be mg. Does anybody see what I've done? That's your normal force. That's your apparent weight divided by your actual weight. You might be wondering, why am I calling this your apparent weight? Because if you were, I had talked about it before, if you're standing on a bathroom scale, it'll read more, right? That's the normal force. Why do you feel like you weigh anything right now? Yeah, that's because the chair is holding you up. What if I pull the chair out from under you? What would happen? You'd fall. So what do you feel you weigh? Watch this. I take the bathroom scale, I strap it to my feet, I get to the high dive, I hop to the edge of the high dive, and I jump off. What does the bathroom scale read?
0.
Well, then what do I feel like I weigh?
Weightless.
I feel weightless. I feel 0 G's.
You feel the.
Do I actually still have gravity pulling me down?
Yes.
Yeah, but there's nothing holding you up. So when you drive your car and you go over a bump and you get that funny feeling in your stomach, that's because you're feeling
0 G's.
maybe 0 G's, it could be that low. Your stomach is floating around in there. Astronauts feel that all the time. Do you understand what I'm saying? Okay, so you feel you have weight because something's holding you up. You take that out from under you and then you're going to be floating around. It would be as if we turned off gravity and you'd be floating around in this room. Yes?
Could you simplify that to 8 plus 2?
Let's do it. The masses cancel out.
What? A plus G over G?
Yes. So could you write A plus G over G? And now can we divide the G into both of those terms? What's A over G? You just write
A over G plus 1.
right. How many people see this? That's another way of calculating your number of G's. What did you tell me you got when you took 640 divided by 490? 640 newtons divided by 490 newtons was 1.3, right? So you're experiencing 1.3 G's. Could you do that with just the A over G? What was the A? Let's plug it in. 3 meters per second squared over 9.8 meters per second squared plus the 1 is what?
1.3.
Hey, it's 1.3 G.
Mr. Goodman,
Yes.
is the G's directly related to acceleration, and like will it always be? Because in this it's 3 and it's 1.3. So if I had 4 meters.
Well, that's just because the 9.8 is close to 10, that's all, okay? So now why are we adding the 1 up here? What is this for?
Gravity.
Right, because we're on Earth. On Earth. If you were in a space station, or if you were in a rocket ship, you're not going to worry about that +1.
That would be undefined.
Let's take a look. Are you ready? Let's try this in a rocket ship now. Who's ready to try it with a rocket ship? Here is my rocket. It's accelerating in that direction. Is there really an up and down in outer space?
Yeah.
No. You float around in your spacecraft. But what if the rocket was accelerating? Where's the floor? That way. If I had a rock and I dropped the rock, this guy is going to see the rock do what? Go that way. What would we see the rock do? It actually could be moving this way or staying still. Let's say the initial velocity was 0. The rock stays still. The rocket ship goes this way. You get it? So he sees the rock falling to the floor. That becomes his floor. Is that wild? You with me? So now what if this acceleration was, say, 4.9 meters per second squared? What would this guy experience? How many G's?
I don't know, most gravity.
Is it half a G?
Right. You take the number of G's is going to be A over G plus 1 if you're on Earth. Are we on Earth?
No.
No, get rid of that. What's he going to feel? How many G's will he experience? 0.5. 0.5 G. Let's put some numbers to this. What if this was a 200-pound astronaut? That's what he normally weighs on Earth. But now he's in the rocket ship. How heavy does he feel he is?
100.
He feels like he weighs 100 pounds. Did you know that's how G's work? If you were experiencing 2 G's, what would you feel you weigh? Double. If you experience 3 G's, triple. He only experiences half a G. He feels he weighs half, 100 pounds if he normally weighs 200. Yes?
But isn't there no gravity in space?
That's why we're not adding the 1.
He's accelerating.
Oh.
Consider it artificial gravity. Like I said, if he had a rock in his hand and he let it go, the floor is going to come up and meet the rock. The astronaut sees the rock falling to the floor. You have to think about
Once
that.
he drops the rock, there's nothing acting on the rock, but he's still.
We're in
accelerating.
space. We're nowhere near Earth or anything, okay?
No, I'm just confused about the equation because where are you getting the G from?
That?
Yeah.
Well, we're comparing what he weighs in the rocket to what he would weigh on Earth.
All right.
Does that make sense? Okay, good. All right. So I hope all of that helped you. All righty. Now, what are we going to do in lab?